Hi everyone, I welcome you to this YouTube channel where we shall be learning physics with IBM. On this YouTube channel, you'll find many lessons ranging from IGCSE AS up to A-level physics. That is physics 9, 7, 01, 02 for A-level, AS A-level, and 0625 for IGCSE. On this YouTube channel, you're going to find a lot, therefore do not hesitate to subscribe, to like, comment, and share the information that you'll find on this YouTube channel. Leave a comment. You can download the video. There is no copyright on it. You can download it so that you can always watch it again and again for easier understanding of the lessons. So I want to proceed from where we stopped last time with AS Physics. But don't forget, subscribe, like, comment, and share the information that you find on this YouTube channel. Okay, so to begin with, I want us to move to where we stopped last time. So we were looking at errors and uncertainties. I said we are dealing with the physics AS. This is 2022, and the syllabus code I think is 9702. That is the physics we are dealing with today. So today I want us to fully understand errors and uncertainties, and especially we shall be concentrating on manipulating errors and uncertainties. Having looked at the types of errors in the previous lesson where we explored the random errors and the systematic errors, recall from the previous lesson that we said a random error normally makes readings to scatter about the true value. Yet a systematic error makes readings to be either above or below the true value by a constant amount. So today we are not going to go back into systematic errors and random errors, but we shall be specifically looking at the treatment of these errors. We shall be concentrating on treatment of these uncertainties or errors. We shall concentrate on the treatment, or if you want to call it combination of uncertainties. You may call it combination of uncertainties. Okay, so let's begin with a general overview. Number one, in order to compare uncertainties, we shall be using either absolute, we shall be using fractional, or we shall be using percentage uncertainties depending on the conditions we face with, or because depending on the conditions we shall always be provided with. Number two, we normally know that an absolute or uncertainty is normally denoted by this symbol here. I think that is read as delta. That is the symbol we are going to use for absolute or actual uncertainties. Many questions that we shall interact with will require the absolute uncertainties. Therefore, we need to make that symbol part of us. Number three, we shall also use a relative, or call them fraction and percentage uncertainties. Of course, since the absolute uncertainties normally have the same unit as the true value or the actual quantity, and yet a fraction is one quantity divided by the other quantity with both having the same unit, then we shall notice that the relative or percentage uncertainties will always have no units. Number four, let's think of a quantity such as x, which has been denoted with its uncertainty as plus or minus 0.1. If we want to denote an absolute uncertainty, the last quantity here is going to be the absolute uncertainty. So the absolute uncertainty in that quantity x is going to be plus or minus 0.01. Number two, if I want the fractional uncertainty, therefore I express the absolute as a fraction of the true value. Therefore, I will divide the absolute uncertainty plus or minus 0.1 millimeters divide by 2. And when I divide, this will be the fractional uncertainty. And number 3, if I want the percentage uncertainty, then it is equivalent to multiplying the fractional uncertainty by 100 so that you express it as a percentage. So there is a great relationship between the fractional uncertainty and the percentage uncertainty. So percentage is simply expressing the fractional uncertainty as a percentage. So when we talk about the way we treat fractional uncertainties will be actually the same way we shall treat percentage uncertainties every time, as we are going to see. Okay. So one important thing is that you should be able to convert to any form as required. This is very important because many times questions will ask you either to write the answers as absolute or to write the answers as percentage uncertainties. There may not be any question which may require you to write the answer as a fractional uncertainty. Therefore, being able to express percentage to fractional, I mean to absolute or absolute to fractional, is very important. So if this is the percentage uncertainty, if we are given, for example, percentage uncertainty in a measurement as say 2%, then it means I can take it back. I could be able to take it back to actually the absolute uncertainty. This means I will just divide 2 by 100 and then I multiply it by that true value or the actual quantity which has been measured. So the resultant here will therefore be in absolute rather than in percentage. And therefore, for the absolute, it will have a unit as opposed to percentage, which is maybe just expressed as percent. Okay, let us look at the basic rules for combining uncertainties. This is very important. The basic rules. So here we shall look at rules that will guide us in combining these uncertainties. These rules are very simple but easy to manipulate because they involve simple algebra, as we are going to see. Rule number 1, if quantities are added or subtracted to give a final result, what do we do to the absolute uncertainties to find the resultant absolute uncertainty? So we simply add, we are going to add the absolute uncertainties only. That is a rule. If quantities are added or subtracted to give a final result, the rule says we only add absolute uncertainties. Remember, absolute uncertainties have the same unit as the true value. Let's look at this example here. They have given us that A is actually 6.5 plus or minus 0.5. The unit is meters. And B is 3.3 plus or minus 0.1 in meters. Every time you are going to notice that the number of decimal places of the true value is always matching with the number of decimal places of the uncertainty. It's not a coincidence because the number of decimal places gives some information about the instrument that has been used for that measurement. So maintaining or having the same number of decimal places is very important. So to begin with, let's find A plus B. A plus B means we are going to begin by adding the true values. Therefore, the true value of P is going to be A, which is 6.5, plus B, which is 3.3. This will give me the true value of P as 9.8. But this question must have required us to include the uncertainty in P. So, because A and B have been added, the rule is saying we add the absolute uncertainties. Therefore, I will say the absolute uncertainty in P is going to be equal to the absolute uncertainty in A plus the absolute uncertainty in B. And when we add the absolute uncertainties, this will be 0.5 plus 0.1, and this gives us 0.6. Because uncertainties can be higher or lower than the most appropriate value, then we shall say that the P should be written as 9.8 plus or minus 0.6. I want you to note, uncertainties are good enough to one significant figure, and the number of the small places of the absolute uncertainty should be the same as the number of the small places of the true value. Of course, if I have added the quantities, it is only because they have the same unit. I can't add or subtract quantities with the different units. So that was for P. Let us see B. Let us see Q. For Q is equal to A minus B. That means I have to subtract A and B. So Q will be equal to 6.5 minus 3.3. And when you press your calculator, I think this gives you 3.2 in meters. So this was also in meters. This uncertainty is also in meters. So that is Q. But then the rule says we only add, we do not subtract uncertainties. That means the uncertainty in Q is going to be equal to the uncertainty in A still plus the uncertainty in B. We never subtract uncertainties. So when I put equal signs here, it means I will have the same uncertainty as before, 0.6. Therefore, I will write the true value of Q as 3.2 plus or minus 0.6. All this is in meters. That is rule number 1. We only add absolute uncertainties if quantities are being added or subtracted. Note that P was being added and Q was being subtracted. The rule says we only add uncertainties. We never subtract uncertainties, whether it is addition or subtraction. Let's proceed. So in general, we have seen that if a quantity x is defined as y plus z, or x is defined as y minus z, and the uncertainties given are absolute uncertainties, as you can see, then the absolute uncertainties in x, or the absolute uncertainty in x, is simply the sum of the absolute uncertainties of each of these quantities. We never subtract uncertainties. But then sometimes we shall be given percentage uncertainties. Then what do we do? Remember, the rule is only applying to absolute uncertainties. That means these percentage uncertainties must be changed into absolute uncertainties, since it is the absolute uncertainties that must be added according to rule number 1. If quantities are given as percentages, then we must change them back to absolute before we add. If the uncertainties for y and z are given as percentages, then these uncertainties must be taken back to absolutes before we add them. We cannot add percentage uncertainties when quantities are being added. Then there is a very important note which I've already emphasized here, that the values are quoted to the number of the small places justified by the uncertainty. Uncertainties are only themselves usually accurate to no better than one significant figure. So normally we shall write uncertainties just to one significant figure, and hence an absolute error or uncertainty should always be recorded to only one significant figure, as giving many significant figures doesn't hold any meaning. So we shall always be quoting absolute uncertainties to just one significant figure. Maybe somebody may be wondering, how do we deal with percentage uncertainties yet quantities are being added? Let me use the same page and give an example. Let us assume that y has been quoted as 2.0 plus or minus 1%, and z has been quoted as, let's say, 4.2 plus or minus 0.5%. And the question is, find x, which is y plus z. So what the rule is suggesting here is that, unlike the absolutes in the previous part which we added, here, since they have given us percentages, we must convert them back from percentages to absolute. So that means I'll find the absolute in x, in y, to be 1 over 100 times 2. which gives me I think this is 0.02, that is absolute, and I will get the absolute in Z, which will be 0.5 divided by 100 times the true value, which is 4.2. And when I press my calculator here, you should also be pressing yours and see that is 4.2 times 0.5 divided by 100. So this is giving me 0.021. That is absolute. Now somebody will say, but teacher, you have written this to more than one significant figure. This is not the final value of x. So I will find x. Of course, x will be the sum of the true values. That will be 2.0 plus 4.2, which will be 6.2. Then the absolute uncertainty in x will be the sum of these two. When I try to find the absolute uncertainty in x, I sum these two. This gives me 0. That will be 0.041. But the absolute uncertainty is good enough to one significant figure. So this will be equal to 0.04. You notice that 0.04 is to two significant figures. Therefore, I mean two decimal places, not significant figures. It is to two decimal places. Therefore, I must ensure that my true value of x is also to two decimal places. So I'll add a 0 here to make it two decimal places. Then I'll write my uncertainty as plus or minus 0.04. So you notice what were percentages. Before we added them, we first converted them to absolute uncertainties before we add them. Okay, I hope that is home and dry. Let's continue. So here I have given an example. Suppose G has been initially calculated to be 9.80645 meters per second squared. That is acceleration due to gravity. And maybe from your calculation, you have calculated the uncertainty in G to be 0.04848 meters per second squared. So how do we record this? First of all, the rule says and the absolute uncertainties are good enough to one significant figure. When I round off this to one significant figure, this becomes 0.05 because this is 8 and this is 4. So I add a 1 to 4 and it makes it 0.05. And you will notice that this is now 2 decimal places. That means my true value should also be recorded to 2 decimal places. That's why you see what was 9.80645 has now been written as 9.81 plus or minus 0.02 meters per second squared. So the number of decimal places for a calculated quantity should always be equal to the number of decimal places of the absolute error. Every time you are recording the final answer after finding the true value and the uncertainty, have that in mind, that the number of decimal places for a calculated value should be equal to the number of decimal places for the absolute uncertainty. Of course, during practical, this last point is talking about what happens during practicals. We shall be calculating many quantities. For example, you'll find t time for 10 oscillations, you find t time for 1 oscillation, and then maybe you may find t squared and so on, t cubed or 1 over t and so on and so forth. In such cases, of course, we shall always maintain. It will always be easier to maintain the same number of significant figures for the raw data. That is, I think, that is maybe when plotting is necessary. However, you can increase the number of significant figures, but we shall see during practical sessions that we can't have less number of significant figures than the raw data. That rule is very, very important. Okay. Rule number 2, and what is deemed to be the most important rule. Rule number 2. For quantities which are multiplied or divided to give a final result, we shall always add the fractional or percentage uncertainties, but note, I've even made note underlined, we shall not add the absolute uncertainties. Whenever we are faced with a quantity, or whenever we are faced with a multiplication and division, we shall only add fractional or percentage uncertainties. Remember, a fractional uncertainty is the absolute divided by the true value or the actual value in the given the expression. Let's see an example. We have that we have to find A times B and include its uncertainty. For simplicity, let's call A a quantity X. Let's say X is equal to A times B, so that it is easier for us to understand what we are talking about here. The rule says when you are dealing with multiplication or division, all you do is to add the fractional or percentage uncertainties. But you look at this particular question that we have been given absolute uncertainties. Then what do? We have been given absolute uncertainties, but the rule is saying we either look at percentages or fractional uncertainties. To begin with, let's begin with the fractional. It means I'll look at the fraction this side and I sum the fractions the other side because we sum the fractional uncertainties. The fractional uncertainty in x will be written as the absolute in x over x itself. The fractional uncertainty in a will be written as the absolute in a over a itself. And the fractional uncertainty in b will be written as absolute in b over b itself. But the rule says we add the fractional uncertainties, so I am not multiplying, I must add the fractional uncertainties. So let's try to find what absolute in x is. In this case, it is equivalent to saying that absolute in x is going to be equal to the absolute in a, which is 0.02 divided by that is 2.34, then plus absolute in b, which is 0.1 divided by 6.0, but note this must be multiplied by the value of x. By the way, what is x? Let's try to find x here. X is going to be the true value of a, 2.34, multiplied by the true value of b, which is 6.0. And my calculator is giving me this is 14.04. You can also check yours. Since a has been quoted in meters and b has been quoted in meters, when I multiply them, this unit will be meters squared. So it means I have to multiply this by 14.04. So when I simplify this bracket and I multiply by 14.04, this is actually giving me the absolute uncertainty in x to be 0.354. You can verify and see. But remember, it should be to one significant figure. So this is approximately 0. Rounding off this to one significant figure. The first non-zero digit is going to be 0.4. That means if I am expected to write the final answer of the result of a times b, then it means a multiplied by b, or x, which is a times b. Since this is one decimal place, I'll go back and write this to one decimal place. So this will be 14.0 plus or minus 0.4. So this is going to be, of course, in meters squared. So we have applied the rule. We have applied it on multiplication. It is the same rule on addition. I mean on division. By the way, I would have used the percentages, but there is no difference with the percentages. Why? Because if I try to consider percentages, let's check. Absolute in, I think in my next slide, I have enough space to deal with percentages. So let me move to the next slide. Method 2, this is an alternative method where we would have used percentages. Remember, percentage uncertainty is the absolute over the true value times 100. In other words, it is actually simply the fractional times 100. Let's try again and see. Let's say x is equal to a times b as required before. And when I try to establish the fraction uncertainties, I'll have that uncertainty in x over x is equal to uncertainty in a over a plus uncertainty in b over b. That is, those are the fractions being added. When I multiply both sides by 100, this side by 100, it becomes percentage uncertainty in x. When I multiply this by 100, it becomes percentage uncertainty in a plus percentage uncertainty in b. So it means I can just get the fraction uncertainties and multiply each of them by 100. Let's check and see what happens. So percentage uncertainty in x is going to be the absolute in a, which is 0.02 as before, divide by 2.34, then times 100. My calculator is giving me 0.86% plus for b, which was 0.1, divide by 6.0. My calculator is giving me 1.67%. So this is going to be the total percentage uncertainty in x. And when you press your calculator there, it will give you approximately 2.5, excuse me, approximately 2.5. I think without rounding off, it is 2.5. Without premature rounding off, it is 2.54. I mean 2. Or if I just consider these values, it is 2.53%. Of course, for the percentage uncertainty, there is no rule on the number of significant figures used. So you just simply sum them up and you get the percentage uncertainty. So does it mean I'll write the a times b as 14.04 plus the percentage uncertainty? Not really. The question may still require to write the answer with its absolute. So what do? So it means, again, having got the percentage uncertainty, I must ensure that I express it as an absolute uncertainty. So it means the absolute uncertainty in x will be equal to 2.53, that is the percentage, divided by 100 times the true value of x, which we have already calculated to be 14.04. And when you press your calculator still, you are getting 0.354, which to one significant figure rounds off to 0.4. Therefore, still, the product a times b, or simply x, is still going to be 14.0 plus or minus 0.4. So that will be our value. So in general, we are saying if we have a product, then here we deal with only fraction uncertainties or percentage uncertainties. By the way, the same thing happens to division. The same thing applies to division. In fact, the uncertainties, the sum of the fraction uncertainties is always going to be the same for multiplication or division. What will make the answer different is when you multiply by the true value. That's when the answer will be different, because when you have a times b, it's not the same. The value a times b cannot be the same as a divided by b. But the sum of the fractions is going to be the same, or the sum of the percentages is going to be the same. But when you convert and multiply by a times b or a divided by b, then there will be a slight difference in the value of the absolute uncertainties. So this is exactly what we have been dealing with here. You first add the fraction uncertainties, or you add the percentage uncertainties as demonstrated above. I hope that one is understandable. Self-check. Here is a self-check question which I expect every student to try out. You are all attempting this self-check question if you have been following. Maybe just to give you a hint, this is using what we have just studied. That is, it is using the rule number 2, that is product. It is a product because from Ohm's law we know that PD, I'm just giving a hint, PD is equal to I times R, and they want us to calculate the resistance. Maybe I can attempt question 1 and I leave behind question 2. So because resistance is equal to V over I, and they have given us the PDV, they have given us the current with the absolute uncertainties, then we can find the resistance with its absolute uncertainty. First of all, let's substitute the true values, find the resistance. So this will be equal to 6.0 divided by 2.4. And when you press your calculator, I think 6.0 divided by 2.4, that is approximately most likely 8.5 ohms. That is 2.5 ohms, not 8.5. Do I have an eraser here? I don't think so. Okay, I have an eraser. So this is 2.5 ohms. So that is the true value of the resistance, 2.5 ohms. And then we now want the absolute uncertainty in R. So we have been given absolutes in each of the quantities, but here this is division. And the rule says when you're multiplying or dividing quantities, you sum up the absolute uncertainties. You sum up the absolute uncertainties. No, not the absolute uncertainties. You sum up the fractional uncertainties or the percentage uncertainties. Sorry for that. So it means the fraction uncertainty in R over R is going to be equal to the fraction uncertainty in V, that is delta V over V, plus the fraction uncertainty in I. So we are summing up the fractional uncertainties. That means when I multiply both sides by R, I will be multiplying R this side to get the absolute. So the absolute uncertainty in R is going to be, in V we have 0.2 divided by 6.0 plus 0.1 divided by 2.4. This is multiplied by the true value of R, which is 2.5. And when I press my calculator, this is giving me, let me check, pressing the calculator. Okay, this is 0.1875. Remember, the absolute uncertainty is good enough to just one significant figure, so this will be approximately 0.2. Of course, having the same unit as the true value. Therefore, writing this to one significant figure results into one decimal place. So I'll write R as being equal to 2.5 to one decimal place plus or minus 0.2, and these two have the same unit as the ohm. You can also go ahead and check using percentage uncertainties, but since by the time you reach percentage uncertainties, you'll have passed through fraction uncertainties, here the answer is required in absolute uncertainties, then there is no need for you to again convert to percentages. Let's proceed. Self-check, question 2 is yours. Self-check, question 2 is yours. Try to find B over F for the given values above. Remember, we have, for these values, we had our value of A in rule number 2. Remember, A was, let me just quote for you A here so that you solve it very fast. A was 2.34 plus or minus 0.02, and this was in meters. and then B was 6.0 plus or minus 0.1. It was also in meters. So try to use these values to find B over A and include its absolute uncertainty. That will take a few minutes. I can give you 2 minutes. 2 minutes, you try to find B divided by A. B divided by A. And this, you'll submit your answers. You submit your working. I will be interested in you to see your working and your answers. Then try also question number 3. Question number 3, you can pause the video at this point and try to record or write the questions and try to work out number 3A, number 3B, number 3C, and number 3D. So these are the expected answers. These are the expected answers. So your task is going to be, you'll be just trying to check if these are correct by writing the correct method and pressing the calculator to verify if those answers are correct. So that is your self-check that you should attempt and submit. Rule number 3, and the most beautiful and interesting rule. For multiplying a number by a constant, there are 2 rules, depending on which type of uncertainty you are working with at the time. There are 2 rules in one. 2 rules in rule number 3, if I'm to put it like that. It will depend on whether you are dealing with absolute uncertainties or you are dealing with fractional uncertainties. Let us see. So if I am dealing with, in part A, let's assume you are dealing with absolute uncertainties. And let's consider a quantity x equals to 3.0 plus or minus 0.2. How do I find the absolute uncertainty in a quantity y, which is defined as 2x? The question is saying determine y and its absolute uncertainty. So, what does the rule say here? So, if I am dealing with absolute uncertainties, you and me can notice. You will notice that 2x, I can write y as 2x, or I can write y as x plus x. Y can also be written as x plus x. What does that mean? I've already gone back to rule number 1. Because it's like I'm now adding x plus x. That means I am going back to rule number 1. And rule number 1 was telling me that when you add quantities, it is as good as adding their absolute uncertainties. Therefore, I'm saying that the absolute uncertainty in y is going to be the absolute uncertainty in x plus the absolute uncertainty in x. To be precise, the absolute uncertainty in y is going to be twice the absolute uncertainty in x. Remember, it was 2x. And now we have 2 times delta x. In other words, twice the absolute uncertainty. So, if I am dealing with the absolute uncertainties, the rule is telling me I can multiply the constant by the absolute uncertainty. The rule is saying when you are multiplying a number by a constant, or if we are multiplying a constant by a given quantity, then we can always multiply by that constant with the absolute uncertainty. Let's check. So x has been given as 3.0. The true value of y is going to be 2 times 3.0, which is going to give us 6.0 in meters. So the absolute uncertainty in y is going to be twice the absolute uncertainty in x, which gives me plus or minus 0.4. Therefore, we shall say that y is going to be equal to 6.0 plus or minus 0.4 in meters. We have simply added the absolute uncertainties, or we have actually multiplied the constant 2 by the absolute uncertainty to find the total absolute uncertainty when y is defined as twice x. So in this case, the uncertainty is multiplied by the constant. Remember, I said there are two rules in one. The first one we have seen when we are dealing with absolute uncertainties. Then suppose we are dealing with um, percentage uncertainties. Let us see what happens. Suppose we are dealing with fraction or percentage uncertainties. Suppose this time x had been defined as 3.0 meters, but this time given a percentage uncertainty. So we want to determine y with its absolute uncertainty. How do we therefore handle this? We want to determine y with its absolute uncertainty. So in this case, the true value of y still remains the same. So we shall say that y is equal to 2 times 3.0, which still gives you 6.0 meters. That is y. But then the percentage uncertainty or the fractional uncertainty is not going to be multiplied by a constant. In fact, the constant does not affect the percentage uncertainty. Therefore, the true value of y is going to be equal to 6.0 meters plus or minus 1.0%. I am repeating this. If you are dealing with the percentage uncertainties, the constant does not affect the percentage uncertainty. Therefore, we cannot multiply the constant with the percentage uncertainty. Let's check if we take it back to absolute. So the absolute uncertainty in y will be equal to, first remove the percentage, that is 1.0 over 100. Sorry, I have to look for an eraser. So it will be 1.0 divided by 100 times the true value, which is 6.0. Let's see what we get here. So here it means the absolute uncertainty in y will be equal to 6 divided by 100, that is 0.06 in meters, of course, because it is absolute. That means the true value of y will be written as 6.0, but remember, to one significant figure, these are two decimal places. Therefore, this means we shall add a 0 here, plus or minus 0.06, so that there is uniformity in the number of decimal places. So you notice, if we are given percentage uncertainties, the constant in front of 2 of x does not affect the percentage uncertainty. The constant in front of x does not affect the percentage uncertainty. Now, somebody will be wondering if the constant is a fraction. Somebody might be wondering if the constant was a fraction. For example, we have p being defined as 2x plus y over 3. P has been defined as 2x plus y over 3. One, there is a constant, which there is a coefficient in front of x, which is 2, and there is a denominator down there, which is actually 3. So it's like writing P as 2x over 3 plus y, or a third, times y. So it means this is a constant. 2 over 3x, the 2 over 3 is a constant, the 1 over 3 is a constant. Therefore, if I wanted the absolute uncertainty in P, I will multiply 2 over 3 by the absolute uncertainty in x, plus I will multiply 1 over 3 by the absolute uncertainty in y. This would simply give me the same thing as a third into twice absolute uncertainty in x plus the absolute uncertainty in y. So when we are dealing with the constants, if we are dealing with the constants, remember to always multiply the constant by the absolute, but not the percentage. I want to repeat this. Multiply the constant by the absolute uncertainties, but not the percentages. So in general, I said if you have a constant in a given expression where A is a constant in Y and uncertainties in Y and Z have been given as absolutes, then the fractionals are given by that. We have already seen that. But the constant in front has been ignored. When dealing with the fractional uncertainties or percentage uncertainties, the constant in front is ignored. When dealing with the fractional uncertainties or percentage uncertainties, the constant in front is ignored. But when dealing with the absolute uncertainties, the constant in front is multiplied by the absolute uncertainty of the quantity. I hope that is home and dry. Okay. Rule number 4, and one of the most important and common rules in almost every exam you'll be doing. Rule number 4. So when values are raised to a power, the rule is saying now multiply the relative or fractional or percentage. Of course, relative and fraction is the same because we compare two quantities. The relative or fractional or percentage uncertainty is going to always be multiplied by the power. A good example, let's have x being defined as 2.0 plus or minus 0.1. The units are immaterial at this point. We don't need them. Okay? So if y is given as x squared, then the question is saying what is y with its absolute uncertainty? So let us begin. Y has been defined as x squared. Let's begin with the true value of y. So y is going to be 2.0 squared, which when you press your calculator, this gives you 4.00. The units are immaterial at this point. But then note that y equaling to x squared is the same as x times x. This is x. X squared is going to be the same as x times x. Maybe let me write this so that it is very clear to a layman. So y defined as x squared is the same as x multiplied by x. Don't you notice that this takes us to rule number 2, the rule of multiplication? And the rule of multiplication is telling us that when you are multiplying quantities, you add the fractional uncertainties. So this means the fractional uncertainty in y, which is given by that, will be equal to the fractional uncertainty in x plus the fractional uncertainty in x. So you notice that this is appearing twice. So it is equivalent to saying a fractional uncertainty in y is equal to twice the fractional uncertainty in x. So what does this imply? You notice that 2 was a power, now it is multiplied by the fractional uncertainty. So we multiply the power by the fraction or percentage uncertainties. Of course, when I multiply this side by 100, the other side by 100, still the 2 remains there. So we multiply the power by the fractional uncertainty. So let us see. Let us just proceed and see what we obtain here. So it means the absolute uncertainty in y is going to be 2 times the absolute in x is 0.1 over the true value of x, which is 2.0. This will be multiplied by this y here, the other side. So this will be multiplied by 4.00. And when I press my calculator, you can also press yours. When I press my calculator, that is obviously 0.4. So absolute in y is equal to plus or minus 0.4. And this is one decimal place. So I'll go back and write my true value of y to one decimal place. So I'll conclude by saying y is equal to 4.0 plus or minus 0.4. Note that when I multiply this by 100 this side and this by 100, it's just the same as having percentage in y being equal to twice percentage in x. So it means we can also multiply the constant, the power, by the percentage uncertainty in the quantity. We can multiply the power by the percentage uncertainty in the quantity. I hope this is illustrated in the next slide. Let's move to the next page. Yes, in this example now we have x with a percentage uncertainty and y has been defined as x cubed. Y has been defined as x cubed. So let's see what happens. So one, we can begin with the true value of y. Y is going to be equal to 8.0 raised to power 3. And when you press your calculator, 8.0, no, yeah, y has already been determined as 8.0. Y has already been determined as 8.0 because it is x is 2.0 meters cubed. So y has already been determined as 8.0. Y is already determined as 8.0 meters cubed. All we shall be interested in is the percentage uncertainty in y. Does it also remain 1% as we saw for multiplication with a constant? Not at all. Note that y equaling to x cubed is the same as x times x times x. This is multiplication. So it means the absolute in y divided by y would be equal to the absolute in x divided by x plus the absolute in x divided by x plus the absolute in x divided by x, which is equivalent to having 3 times absolute in x over x. So the absolute in y over y is equal to 3 times the absolute of x over x. So if I multiply this side by 100, the other side by 100, this side I now have percentage in y being equal to 3 times the percentage in x. The percentage in y is now 3 times the percentage in x. Therefore, since I have percentage in x, I will conclude that the percentage in y, in my y value is going to be 3 times 1.0, which is going to be 3.0%. So it means I can say that y is therefore equal to 8.0 meters cubed plus or minus 3.0%. So you see here, when you have a power, the power is multiplied by the fraction or by the percentage. Note that very carefully. If I wanted the absolute value of the uncertainty in y, then I can change this from percentage. This is plus or minus. So the absolute uncertainty in y is going to be equal to 3.0 divided by 100 times the true value of y, which is 8.0. I think 3 times 8, that is 224 divided by 100, that is going to be 0.24. Then to one significant figure, this will be equal to 0.2. So it means I will say that y is going to be 8.0 plus or minus 0.2. Okay, so I hope that is well understood. It must be home and dry. Let's proceed. Rule number 4 is continued to deal with square roots. How do we handle square roots? We are almost getting done. How do we handle square roots? So there we have a simple example here. We are going to use the same values of x given above. and we are going to try and see if we can find y equals to the square root of 4. How do we handle square roots? You and me, as a mathematics student or somebody who has been exposed to mathematics, you notice that y equals to the square root of x is the same as x power a half. It is the same as x power a half. So it's like we are now having a power. And previously we have seen what we do with the power. We multiply the power with the fractional uncertainty or with the percentage uncertainty. Therefore, if x has been defined, let's use the previous value of x. X was equal to 2.0 plus or minus say 0.1. So we are using the previous value of x as 2.0 plus or minus 0.1, ignoring the unit. So the absolute uncertainty in y divided by y would be equal to, because the rule says you multiply the power by the fractional uncertainty or the percentage uncertainty, the power here is a half. So it will be a half times the fractional uncertainty in x, that is delta x over x. So if I want the absolute uncertainty in y, this will be a half. The absolute in the fraction in x, which is 0.1 divided by 2.0. Then I multiply by the true value of y. Right from here, y is the square root of 2.0. What is the square root of 2.0? Square root of 2.0. So the square root of 2.0 is I guess it is around 1.414. That is the square root of 2.0. So it means I will multiply here by 1.414 to get the absolute value. 1.414. I multiply this by, you can also multiply 1.414 times 0.1 divide by 4. So this gives me my absolute as 0.03535. To one significant figure, this is 0.04 plus or minus. So it means the true value of y will be written as, these are two decimal places, so I'll also take only two decimal places from here. So it will be 1.41 plus or minus 0.04 as the true value of y. So that is how we treat the square root. It may not necessarily be a square root, it can be any root, it can be the fourth root. So if it is the fourth root, if we are told to find, for example, y is equal to the fourth root, of course there will be 4 here of x. So it means also that the absolute in y over y will be equal to a quarter of the absolute in x over x, as simple as that. So in general, I said if y is defined as the nth root of x, then the fractional uncertainty in y is going to always be 1 over the root times the fractional uncertainty in the quantity. That is the rule on the roots. That is the rule on the roots. Not only square root, it can be any root. So I want you to mark that very carefully. Next. Now, if the percentage uncertainties are given, for example, we have x is defined as that. So the rule is still saying you either multiply the power by the fractional uncertainties or you multiply the power by the percentage uncertainties, because for this particular expression, y is equal to x power a half, which we have seen already as 1 point. This has already been seen as 1.414. Then fractional uncertainty in y over y is equal to a half fractional uncertainty in x over x. If I multiply this by 100 and this one also by 100, this side I have percentage uncertainty in y being equal to a half into percentage uncertainty in x. And they have given us the percentage uncertainty in x as 1.0. That means the percentage uncertainty in y will be a half. Remember, a half was a power. So this will be a half times 1.0%, which gives you 0.05%. Therefore, that will be the percentage uncertainty in y. If the absolute is required, now I have to take it back to absolute. So it means I will have the absolute in y will therefore be 0.05 divided by 100, of course, times the true value of y, which is 1.414. So you have 1.414 times 0.05. Is that 0.05? Not really. That is 0.5, I guess. This is 0.5. 0.5. So it is 0.5 times 1.414 divided by 100, and this is giving me how to remove the rubber. So this is giving me 0.007 to one significant figure, of course. That means these are 1, 2, 3 decimal places. So my acceptable value of y will be written as 1.414. Those are 3 decimal places, plus or minus 0.007. I hope I calculated it correctly here. A half of 1.0 is 0.5. Then changing it to a percentage, from percentage to absolute, it gives me that. So that is how we shall be dealing with square roots or roots in general, not necessarily square roots, but roots. And then next, the inverse. What do we mean by inverse? I think the precise way of saying inverse is reciprocal rather than inverse. But suppose you have quantities such as 1 over x or 1 over x squared or 1 over the square root of x squared. Let's begin with 1 over x. So you will notice that if y is defined as 1 over x, this is the same as x power negative 1. Now it means the rule of powers will be used here. Or you can say this is the same as x power 0 divided by x power 1. So it's like you are dividing x power 0 by x power 1. Let me take this because it's the easiest to understand. Because when I use this, people will end up subtracting uncertainties, yet uncertainties are never subtracted. So this is division because it is x power 0 is 1, and then divide by x power 1. Because of division, we said we add the fraction uncertainties. So let's see. So it means I'll look at fraction uncertainty in y over y being equal to the power is multiplied by the fraction uncertainty. So this will be 0 times delta x over x plus the power is multiplied by the fraction uncertainty. So this will be 1 into delta x over x. So it's like we are multiplying this fraction uncertainty with 0. So it is equivalent to having delta y over y being equal to just delta x over x. So do not confuse y is equal to x with y equals to 1 over x. Do not confuse that. Do not confuse y equals to x with y equals to the 1 over x. So we are seeing that if it is 1 over x, the fraction uncertainties are going to be expressed like that. So you can also predict that for y equals to 1 over x squared, it means that y is equal to x power 0 divided by x power 2. It's now you treat this as division. When you are dividing, you add the fraction uncertainties, but again they are powers. When you have powers and you are dealing with the fraction uncertainties or percentage uncertainties, you multiply the powers by the fraction uncertainties, or by the percentage uncertainties. Therefore, the absolute uncertainty in y over y will be equal to 0, absolute uncertainty in x over x, plus there is a power here and the power multiplies the fractional. So this will be plus 2 absolute uncertainty in x over x. That means the absolute uncertainty in y over y will be equal to twice absolute uncertainty in x over x. As simple as that. So you see this was a power in the denominator. Similarly, you can predict for the last one that if y is defined as 1 over root x, you can now predict that the fractional uncertainty in y is going to be simply a half times, it is simply going to be a half times the fractional uncertainty in x over x, because the power in the denominator is power half, which is the square root. So you are going to notice that if y is equal to 1 over root x, the fractional uncertainty is the same, or the percentage uncertainty is the same as y equals to x, y equals to square root of x. I hope you have noted that. So we conclude by saying that we treat inverse functions the same way we treat quantities raised to power, because they are actually raised to a negative power. Though we ignore the negative, since uncertainties can never be subtracted. Please and please, please never subtract uncertainties. I beg of you, never subtract uncertainties. Okay, I think we now qualify to move to the last rule, rule number 5. This rule deals with logarithmic quantities. Unfortunately, you will not find this rule in AS papers. But of course, for completeness, we can look at it here. You'll basically find this rule in A-level papers, especially paper 5. There's a question called analysis, which is question number 2. But since we want to complete we want to complete a combination of uncertainties and errors, or treatment of uncertainties and errors, we can also talk about dealing with logarithmic quantities. When I talk about logarithmic quantities, I mean ln and log of x. So let's begin. We are given an example x as 2.0 plus or minus 0.1 in millimeters, and we want to find ln with its uncertainty. So of course, finding ln is very easy. One, you can find the ln of the best value. So you say ln of the best value, or the true value, which is ln of 2.0. And ln of 2.0 we normally press ln of 2.0. I think it is 0.693 to 3 significant figures. That is ln of the best value. Next, you can find ln of the maximum value, or the highest value. The highest value of x is expected to be 2.0 plus 0.1, which is going to be the same as ln of 2.1. That is the highest value of x we can have. And when you press your calculator, I think this is approximately 0.742 to 3 significant figures. Therefore, if I want the uncertainty, the absolute uncertainty in ln of x, it is simply going to be the difference between these two values, that is 0.742 minus 0.693. And when you subtract, this gives you 0.049, which is approximately 0.05, because uncertainties are good enough to one significant figure. But then when you write this to one significant figure, you come up with one decimal place. That means, two decimal places actually. You have two decimal places. That means the accepted value of ln of x will be written as ln of x is going to be equal to 0.69 plus or minus 0.05. Of course, here I can't put a unit because ln is a ratio, so I cannot put units here. The same thing would have happened if we were to use logarithm. If the question wanted log of x, I would get the log of the best value, I get the log of the maximum value, and then I subtract. By the way, this can also be applicable, it can also work to minimum values. Let us assume the log of the best value, the ln of the best value, that is 2.0, is 0.693. Then let's find now ln of the minimum value. Minimum value means 2.0 minus, because remember this is plus or minus. So I'll say 2.0 minus 0.1, which gives me ln of what is that value? That is, I think, 1.9. And when you press your calculator to find the ln, it is 0.642 to three significant figures. So it means the absolute uncertainty in ln of x is going to be the difference. This time I'll say 0.693 minus 0.642. When you subtract, this is giving me 0.051. And when you write one significant figure, it is approximately 0.05 as before. So still, you notice that ln of x will be the same. I am saying the same approach is used if log of x is to be found. Log of x, ln are treated the same way. For those of you who didn't know, when somebody says ln of x, this person is referring to log, but this time not to base 10, but to base e of x. Log to base e is what we call ln. So do not think that is different. So if it is log to base 10, you've treated the same way we have treated we have treated ln. I think that has been an interesting rule, and it is I think it is the simplest rule that you will find in paper 5. So at this point, you therefore qualify to attempt the following self-check. Number 1. Question number 1, you have y equals to kml cubed over wt cubed, where k is a constant. They have given you L, they have given you M, they have given you T, they have given you W. Which measurement contributes most to the uncertainty in a calculated value of y? Find the answer to that question. Which measurement contributes most to the uncertainty in a calculated value of y? Number 2, they have given you the expression for finding the density. They have given you quantities such as the mass, the length, and d is the diameter, I think. What is the percentage uncertainty in density? Using both rule number 2 and rule number 3 or rule number 4, you should be able to get the percentage uncertainty in the density. In fact, you can even go ahead and deduce the absolute uncertainty in the density. Note that here, the quantity is given, mass is in grams, L is in centimeters, and there is no specific unit dictated here, so you can even use centimeters. You convert this back to centimeters so that your answer for density is in grams per centimeter. But of course, when you're finding the percentage uncertainty, I don't think you need a true value here. Next, number 3, they have given you V as TL over M. V is most like the speed, and T is most like a tension, L is most like a length, M is most like the mass. Calculate V with its absolute uncertainty. So here they have given you percentages. Then they have even given you the square root. We have seen how to handle the root. We have seen multiplication because there is T times L. We have seen multiplication and division, how shall we deal with this and come up with the final answer. Next is number 4. Number 4, here they have given you an expression for volume. The diameter has been given, the length has been given, and the mass. You are going to calculate the density with its absolute uncertainty. And you must give your answer to an appropriate number of significant figures. Remember, for the absolute uncertainty, its number of significant figures is 1. Appropriate. Then after establishing the number of significant figures of the absolute uncertainty, now you should look at the number of decimal places to which the final value should be written. I hope that is also very clear. Next is number 5. Determine the density of iron given the measurements below. They have given you the mass, they have given you the diameter of a sphere. In other words, it's like iron is in a spherical shape. Of course, for those of you who don't know, for completeness, because you'll be finding density from mass over volume, and they have given you mass with its absolute uncertainty, but they have not given you the volume. You know that the volume of a sphere is 4/3 pi r cubed. You don't know the radius, you have the density, so you substitute again. It becomes 4/3 pi. Where there is the radius, I put d/2, and this is raised to power 3. And when you simplify this further, you will notice that this becomes pi d cubed over 6. In other words, the density, the formula you'll be using for the density will be, because when I substitute for V with this expression here, the 6 goes up. So it becomes 6m over pi d cubed. So you will now use this expression to find the density with its absolute uncertainty. Note, it is always wise to manipulate the expression or the formula so that you only include quantities whose absolute uncertainties have been given, rather than just substituting the mass and separately calculating the volume and substituting so that I find the density. I went ahead and simplified the expression for volume so that I bring in the quantity whose uncertainty is given, so that when I substitute, it becomes easier for me to find the absolute uncertainty. So using this expression, you should go ahead and find the density. Lastly, the mass, number 6, the mass m of a metal sphere is given by the expression pi d cubed rho over 6, where rho is the density of the metal and d is the diameter of the sphere. The data for the density and the mass are given in the table below. Calculate the diameter d, including its absolute uncertainty. So everything you need has been given, including the formula. So all you will need is to make the diameter the subject. In other words, the diameter will be equal to the cube root, I guess, cube root of 6m divided by pi times rho. Because m has been given with its uncertainty, rho has been given with its uncertainty, percentage uncertainty, then remember the rules of the power, remember the rules of the root, remember the rule of division, remember the rule of the constants, and you should be able now to come up with the density and its absolute uncertainty. I think you should be able to do this, and when we meet, must be able to submit that work. I guess it has been a very good engagement. Wherever you are, you must have followed to this end, and at least you must have tried to understand the rules involved in combining uncertainties, and therefore the next time you find such questions, you should be able to answer them with confidence. Thank you for watching. That's the end. Bye bye, but don't forget to subscribe. Bye.